Hello, I'm Wesley Hutchins, and today I'm part of a group that has just made a genetic algorithm to evolve virtual creatures, and I'm here to show you our algorithm. Basically, if we look at the algorithm right here, this is our complete GUI that shows the results of our project. What we've done is we've made a genetic algorithm that evolves creatures to jump within a virtual environment, provided a physics engine. As you can see from this initial population, the creatures are various sizes and shapes. And when you animate them, they will jump within that environment. Our goal today is to make these creatures jump as high as physically possible within this applied physics engine. And to do that, we have implemented two different types of algorithms to accomplish our goal. First, there's a hill climbing algorithm, which we'll have Matt, one of my other group mates, talk about here shortly. And secondly, we have a genetic algorithm that combines creatures just like real creatures would combine in biology. The genetic algorithm works by splicing together different traits from two creatures to produce a new creature, and then the fitness is evaluated by running them through the physics engine to see if they've improved or not. To keep the population diverse, we also match up the differences between creatures so that our population doesn't end up looking too similar too quick. This algorithm is designed to run for an extended period of time to get maximum results, and therefore we had to make sure that it was very tight in terms of not being able to have memory leaks or any sort of exceptions being thrown. We ran it overnight for 24 hours on an 8-core machine to produce some of the best creatures that will be shown today.
I'm Matthew, and I worked on the hill climbing part of this genetic algorithm. The purpose of the hill climbing genetic algorithm is to explore the search space of the creatures. For our genetic algorithm, what I did was initially it goes through every creature in the population, and it will iteratively go through every block and make some small change, and if that change gives you an improvement in fitness, it will keep that change and continue making that change until it no longer makes an improvement. After a while, after a creature's been hill climbed over and over, the idea was to save time and hill climb that creature for less time, so you eventually just start going through one gene of a creature every iteration of the hill climb.
Hi, I'm Caleb Miller, and I did the graphical user interface and statistics for the creature evolution program that we worked on. I'm going to be showing you today some of the creatures and how they've evolved, what they look like, how they move, and what kind of statistics we can gather from them. That way we know what we're looking at and if we're solving the problem or not. You see here I went for a 2-window system. That way we could see the creature world. Is any size we wanted it. That way we can. And in our creature world we have some basic zoom in and out controls that we can look up and down. And this becomes useful for creatures that jump very high. This is our tool pane, and we can select the number of tribes for the genetic algorithm. It runs 1 tribe per CPU core. So you can see we have 8 tribes here for 8-core machine. This is our creature select slider. It selects creatures based on best fitness being at the front and worst creatures being on the back. So this is one of our best creatures right now. However, the genetic algorithm has not been run, so this comes from the initial population. This is one of our worst creatures in this tribe. So if we animate this creature, you see it doesn't do what it's supposed to. It doesn't jump at all. It just kind of rolls up on its side. So this creature will either be deleted or marked for hill climbed, and hopefully we see an improvement. If we come over to one of our better creatures, we see this one actually does jump. If you'll notice, the physics engine is not true to life physics. It's kind of interesting, but it does do some movements and it does jump up. If we come over and look at our stats pane, we can see the currently selected tribe and the current creature normalized fitness. This normalized fitness is the best fitness of this creature in simulation time in the algorithm itself. Whereas down here, the current simulation animation fitness is the fitness of the creature as you're seeing it being animated. The highest fitness score in the tribe is the best creature in that selected tribe. As you see, if we go to a different tribe, it has a different fitness. This creature happens to be a whole lot better than the last one. And our current hill climb generations and genetic generations, those are the sum of generations that have happened since we have started our algorithm. So now I'll pause this guy and I'll start the algorithm, and we can see on the screen some of these creatures get bred and hill climbed into something that hopefully will give us a better fitness. Go ahead and start it now. So you see we're getting not going too quickly here. It's probably because of my slow computer. We're getting about 20 generations per second. On a faster machine, I've seen it get as high as 40 and even 100 generations per second. Really depends on the size of the creatures, population, many other factors, how complex things are. Eventually the populations will change.
I'm gonna cut it.